first data sequences, some that don't fall into either category. There's still a pattern, but it's not necessarily going to be adding the same thing every time to be arithmetic, and it might not necessarily be multiplying by the same thing every time. So this symbol is new. This is a Greek letter sigma. And what it means is summation. So sometimes this is called summation notation. You see the word sum in there. And other times it's called sigma notation because that's what letter that is in the Greek language, yeah? What? Not in this context. In this context, it's much simpler than that. So this just means that you're going to find the first term through the sixth term and then add them all together. So you're going to find the first term by plugging in a 1. You're going to find the second term by plugging in a 2. So when you plug in a 1 for the first term, and I'll just do a sub, you plug in a 1, you get 1 squared plus 1 over 1, which is 2. So your first term is 2. Then you're plugging in a 2. That's going to be 2 squared plus 1 over 2, which is 5 halves, or 2.5. Then you're going to plug in the third, an m of 3 to find the third term. 3 squared plus 1 over 3 is 10 thirds. Then you're going to plug in the fourth. That's 16 plus 1, 17 fourths. A sub 5, plug in a 5, you get 5 squared plus 1 over 5, which is 26 fifths. Whew. And the sixth term, which is 6 squared plus 1 over 6, 37 sixths. So you've got your terms 1 through 6. The sigma notation in math just means add them all together now. So I'm going to take all of these and add them. And my answer, this will be all calculator, 2 plus 2.5 plus 10 thirds plus, what is it, 17 fourths plus 26 fifths plus 37 sixths all at once, 23.45. And that's your answer. Okay, the next one doesn't start with the first term. It wants you, it wants you to start with the fourth term, plug in through the seventh. So you'll find the fourth term, the fifth term, the sixth term, and the seventh term, and then add them all together. Okay? One thing, there's a mistake on this one. If this says j equals 4, this x should have been a j to match that. So you'd plug in a sub 4, a sub 5, a sub 6, and a sub 7, and then add them all together. We're not going to do that for the sake of time. Okay? I want you to look at number 4. If I need to plug in a 5 for the n, and then a 6 for the n, and then a 7 for the n, and so on, and there's no n, what happens if I plug in 5 to that function? What do I get? What do I get? Nathan? Was that a hand or was that a stretch? Oh, sorry. If you're trying to plug in a 5 for an n and there's no n to plug it in for, then you're just going to get 3 when you plug in a 5. When you plug in a 6 and there's no place to plug in a 6, you're still going to get a 3. All the way through a sub 10, when you plug that in, you're still going to get a 3. This is kind of a trick question. It's not really meant to be. It's just, unfortunately, what happens with numbers. If you're plugging in terms 5 through 10, how many plugins is that? 6. Does that make sense? What if you plugged in, just a side question, what if you plugged in from 11 to 25? How many plugins is that? Yes, Isaiah, 15, correct. The trick with that is people try to take the difference And that would lead you to say 14 terms. But you're counting both the 11 as a plug-in and the 25 as a plug-in. So it's the difference plus one more because you're plugging in both endpoints. So that's a little bit tricky. This says, what type of series are each of the examples above? Meaning arithmetic, geometric, or neither. Is this adding the same thing every time? Or multiplying by the same thing every time? No. That's neither. Okay? This one, just look at the rule. Is that linear or exponential? Linear. So this one's arithmetic. This one's not linear and it's not exponential. What's this one? Geometric, because the variable is in the exponent. Do you know what this keeps multiplying by every time? What the common ratio is? 2. Very good. R equals 2 because that's the base of your exponent. Do you know what the common difference was back in number 2? No, 3. 3. The slope is the same as the common difference. Okay? So if you looked at those plugins, you would see it better if you had the plugins laid out in front of you. But the slope is your common difference, and the base of your exponent is your common ratio. What about this one? Is that linear or exponential or neither? What'd you say, Maggie? It's linear. Y equals 3. That's a flat, it's horizontal line, so it's kind of a special one. But this is arithmetic, and what's the common difference? What's the slope of a flat line? What are we adding every time? 0. Okay? So that's kind of a tricky one. So we're given a couple sequences here, and we're asked to rewrite each using sigma notation. So, can you see a pattern here? What's the pattern here? Nate? Okay, so 3 is being raised to some power. I'll just say k. So where is this starting? What would k have to be to give me my first term of 3? 1. K would have to be 1 because 3 to the first power is 3, right? And what would k have to be? 3 to what power would end me at 243? 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, 3 to the fifth. So you're plugging in 1 through 5, and you've written that. Okay, let's jump to 8. Something that's a little less obvious. What's the pattern here? The numerator keeps increasing by 1, right? So I'll let that be n plus 1. And the denominator starts at 2. So what am I going to start n at if I want my numerator to start at 1? 0. So what would the denominator have to be in order to get me to 2? N plus 2. Very good. See that? This isn't the only option. There's definitely different ways to make something happen. But if I start with 0, I'll have 1 over 2. So that's good. What would I need to end with in order to make 5 over 6 happen? 4. N would have to be 4 in order to make the numerator 5 and the denominator 6. I think that last one we will wait on the last one. We'll just do this middle one. Does anyone see the pattern here? What did you say? Add 5? No, 1 plus 5 would have brought us to 6. It's not arithmetic because I'm adding 3, adding 5, adding 7. So it's not arithmetic. I'm not adding the same thing every time. I'm multiplying by 4, and then I'm not still multiplying by 4 to get to 9, so that's out too. So it's not arithmetic or geometric. Try to think differently. Yes, I think we could quantify that with a formula, but I think that'll be harder to do. There's some easier way of looking at it, Andrew. 1 squared, 2 squared, 3 squared, 4 squared. So we're squaring something every single time. That's just changing, because at first we're squaring 1, and what's the last thing we're squaring? 5. So that wouldn't be arithmetic or geometric. It's still a sequence, still a pattern, but it just doesn't fit into arithmetic or geometric. Neither did the last one, for that matter.